Question, how can three-dimensional vectors be expressed? So let's say we have vector A and it has an x component, a sub x, and it has a y component, a sub y, and a z component, a sub z. So vector A can be expressed a sub x times unit vector I plus a sub y times unit vector j plus a sub z times unit vector k. Now, we're always going to agree to use a right-handed coordinate system. So if you draw the x-axis and then you draw the y-axis, the positive z-axis will always be found by taking your right hand, putting your fingers in the x direction, curling them towards the positive y, and your thumb would point in the direction of positive z. So it's hard to draw that, so if I just draw it like at a 45-degree angle down here, sometimes it gives the illusion of a three-dimensional diagram. That would be positive z. Notice if I tried to do that with my left hand, if I put my left hand in the direction of positive x, and then curl my fingers towards positive y, my thumb would go into the page. But by agreement, we always use a right-handed coordinate system. Now, we could use this as drawn, but sometimes I find it easier to draw the right-handed coordinate system a different way. So what I'm going to do is I'm going to erase these, or I'll just erase the whole thing. Whoa. I got to lower that eraser. It's turned up. All right. Too small. Just right. I'm going to let this be my positive x-axis. This is going to be my positive y-axis. And then straight up is going to be positive z. Notice it is a right-handed coordinate system because if I put my hand in the direction of x, curl it in the direction of positive y, my thumb points in the direction of positive z. So let's say a sub x was 3 units. I might count off 1, 2, 3 in the x direction. And then this here would be the component of A in the x direction. Or I could write that as a sub x times unit vector I. And then maybe a sub y is 4 units. So moving to the right in the y direction, I might come across here 1, 2, 3, 4. I'm just making up any values. And if I draw a vector in the direction of positive y, that there is a sub y times unit vector j. Notice that's in the xy plane, like that's on the flat plane. But that only gives the two components. So now I got to find a sub z. So if I rise up, and let's say it's 5 units. 1, 2, 3, 4, 5. And I draw an arrow in that direction. A sub z times unit vector k. Notice those three components are in head-to-tail form. So if I draw a resultant vector from the origin, headbutting the last vector drawn, that would be my vector A. Now, it's hard to draw these because they're three-dimensional, and we're drawing a three-dimensional situation on a two-dimensional paper or screen. What you need to realize is if you had a ruler and you measured the length of vector AX or AY or AZ, the length of the arrow used to represent the vector A, the whole shebang thing, should be the longest. Since all three of these were positive coordinates, it might not look like the longest in my diagram, but if it was actually drawn out three-dimensional, if it was actually a three-dimensional scale, it would be the longest. So by knowing what AX, AY, and AZ are, I could describe vector A in this three-dimensional space. And those, of course, are known as rectangular coordinates. Now, you might recall that if we had a two-dimensional vector, like this vector here, if we wanted to find the magnitude of that, we could use Pythagorean theorem, and the magnitude of this vector A right here can be found by taking the square root of the two components squared. The square root of the sum of the components squared. Well, interesting enough, but definitely not directly obvious, if you want to find the magnitude of that vector A right there, the magnitude of vector A, written like this, if you were drawing the scale, the diagram to scale, a one-to-one scale, it would be like the length of the arrow. Sometimes it's also just written as A, without the arrowhead sign. The magnitude of vector A, similar to before, it's the square root of the sum of the squares of the components. But now there's just three of them. Now, every so often, I have to go back and prove that to myself because it's definitely not obvious and it kind of bothers me. Like, how the heck does that work out? But it's not that difficult of a proof. I urge you to try to prove this to yourself. If you go back and you put AX and AY in head-to-tail form and you draw a vector from the origin to the head of AY, sometimes that's called vector R. you can find an expression for r in terms of ax and ay using Pythag. Easy enough, yes? That's what all the cool AP students say. And then once you have an expression for r in terms of ax and ay, you can find an expression for the magnitude of a by using Pythag again with r and az. So prove this to yourself, that the magnitude of a three-dimensional vector, is the square root of the sums of the squares of the components. Now, sometimes that vector is expressed in terms of spherical coordinates. You need 3 this time because it's a three-dimensional scenario. If you want to describe vector A in terms of its spherical coordinates, the spherical coordinates are rho, theta, and phi.
So those aren't called.
How do you pronounce this?
So, rho is just the symbol for the magnitude of vector A. You know, this length right here. The magnitude of vector A, that's what rho is. It's an italic symbol. It's a Greek symbol called rho. It looks like an italic P. It's pronounced rho. It's also the symbol for density. We'll be using it a lot this year. It's also the symbol for resistivity, which we used last year in the, yeah. Theta is the angle between A sub x and that R arrow that we drew right here. So this little angle right in there. Maybe I should make it bigger. This angle right in here. That's theta. And that's like the theta when we were doing polar coordinates. You have to first draw R, which is the resultant of AX and AY, and theta is the angle between AX and R. Whoa, too small. Whoa, too big. And then phi is the third thing you'd have to state. And going back to my diagram, phi is the angle between the positive z-axis and vector A itself. It's not in the plane of any of the coordinates. It's not in the xy plane, nor is it in the yz plane or the xz. It's, you know, it's coming out three-dimensionally right here. But from the positive z, right over there, to the A vector itself, that's phi. And it's like an O with a line down there. It's a lowercase phi. So if I had two vectors, vector A equal to AX times unit vector I plus AY times unit vector J plus AZ times unit vector K. And then I had a second vector, vector B, where B sub x is the component of B in the positive x direction. So it would be sub x times unit vector I plus B sub y times unit vector J plus B sub z times unit vector K. If I want to find the resultant of those two vectors, I could use the component method. Vector A plus vector B, it's going to be some expression times unit vector I plus some other expression times unit vector J plus some other expression times unit vector K. And Nikhil, what would be that first expression times unit vector I? Yeah, you know, you just add all the components going the same direction together. And remember we took the sum of all the forces in the y? How would we write that out, David?
A sub y plus b sub y.
And likewise, we would add up all the components in the z direction. A sub z plus b sub z. So as soon as you know the components, you can easily write the resultant just by adding up the components. Now, if you wanted to get the magnitude of vector A plus vector B, it would be written like this. And this is what we'll end this first period on. It's the square root of the sum of the squares of the components. But now the components are ax plus bx. So here it would be ax plus bx squared plus AY plus BY squared plus AZ plus BZ squared. All right, and this is a good place to pause.